Hello, I'm Ray of the Ray Code. In this video, I'll be studying the design pattern known as factory. I'll be using C++ in this video. I use other programming languages to study this design pattern. For example, I use PHP, Java, and C#. But for this video, I'll be using C++. I provide a list of reasons of why a C++ programmer will want to study this design pattern. I'll give you a UML that was given by the game for. We go through some sample code in this video that you may find yourself at theraycode.org or my GitHub site. I provide a SWOT analysis of this pattern also. I have put timestamps and notes in my notes. Please follow me on X, Facebook, and LinkedIn. Leave a comment, subscribe, but most of all, be good. The factory design pattern deals with the problem of creating objects without specifying the exact class of object that will be created. Instead of creating a constructor directly to create an object, a factory method is employed to create the object. This factory method is typically defined in an interface which is implemented by concrete classes. The pattern is thus about delegating responsibility of object instantiation to specialized methods rather than directly instantiating objects with constructors. Why the factory design pattern is important for the C++ developer. Decoupling. The factory pattern allows for a decoupling of the client code which needs the object from the code that instantiates the object. This decoupling means that changes in one area, like adding new object types, are less likely to impact other areas of the code. Flexibility. By deferring object creation to factory methods, it becomes easier to introduce new object types without changing existing code. The client simply interacts with the new factory or modified factory to get the new object type. Centralized object creation. By centralizing the object creation process, the factory pattern ensures consistency and can lead to easier maintenance. If there's a need to change how objects are created, it is done in one place, the factory. High complex creation logic. Some objects might require intricate setup before they are ready to use. The factory can hide this complexity, ensuring the client receives a fully initialized, ready-to-use object. Dynamic runtime decisions. The factory pattern allows for decisions about which class to instantiate to be made at runtime based on certain conditions or parameters. This brings about a dynamic aspect to object creation. Better resource management. C++ being a language where resource, especially memory management, is crucial, factories can help ensure that objects are efficiently created and destroyed, assisting in resource management. Consistent object initialization. If there are mandatory post-construction steps for an object, e.g. setting certain fields, initializing resources, a factory method ensures these steps are always executed, guaranteeing a consistent state for each created object. In summary, for C++ developers, understanding the factory design pattern provides a powerful means to abstract away the complexities and intricacies of complex object creation, resulting in cleaner and more maintainable and scalable code. UML product defines the interface of objects the factory method creates. Concrete product implements the product interface. Creator declares the factory method which returns an object of type product. We also define a default implementation of the factory method that returns a default concrete product object. Concrete creator overrides the factory method to return an instance of a concrete product. Collaboration. Creator relies on the subclass to define the factory method so it returns an instance of the appropriate concrete product. Hello, my name is Ray. I'm the Ray in the Ray Code. In this show, I plan to give you an example of the creational pattern known as a factory design pattern. We start with creating the product class. This defines the interface for objects the factory will create. We give it the class structure. We add the IO stream at the top. We add a virtual use method. Pure virtual functions are to be implemented by the concrete products. And we add the virtual destructor for proper cleanup. Now, let's work on the concrete product. We start with the class structure. We create the class structure for concrete product A. We extend it with the product class. We implement the abstract method use. And we implement another concrete product B, which is also extended with a product class. Now, let's look at the CPP side. We start with a blank CPP file. We tie it to the concrete product. We implement concrete product A's behavior, and we implement product B's behavior. Now, we define the creator interface. We create the file structure. We include the product.h file at the top, which has our virtual use method requirement. We have the creator class. Inside the creator class, we have the factory method, which returns a product object. And we have the virtual creator deconstructor. Now, let's create a concrete creator, which is the factory implementation. We start with the file framework. We include the creator.h file and the concrete product.h file. We create a class structure for concrete creator A and extend it with the creator class. And then we add a product pointer factory method to override the factory method. We implement concrete product A's behavior. We do the same for concrete product B. Now we add the CPP file for the concrete creator. Here's the file. We include the concrete creator.h file at the top. Factory method returns an instance of concrete product A. The factory method also returns an instance of concrete product B. Now let's go to the main method in the program to do our demo. At the top, we include the concrete creator file, create a factory for product A, and we create a factory for product B. Do some cleanup, compile, and we have using concrete product A, using concrete product B. My name is Ray. Keep coding. SWOT analysis of the factory method design pattern for C++. S strengths. Encapsulation. Highest object creation logic. Reducing dependency on concrete classes in C++. Extensibility. Adding new object types requires extending the factory without modifying client code. Polymorphism. C++ supports efficient use of polymorphism to create objects dynamically. W. Weaknesses. Virtual function overhead. Requires the use of virtual functions, which can introduce minor runtime overhead. Code proliferation. Generates additional classes and functions, increasing the complexity of smaller projects. Manual memory management. Improper handling of dynamic allocated objects can lead to memory issues. O. Opportunities. Game development. Frequently used to generate game entities or levels dynamically in C++. Plugin frameworks. Suitable for building extensible plugin architectures in C++ systems. Cross-platform compatibility. Helps in developing portable object creation mechanisms for C++ libraries. T. Threats. Performance risk. Overuse of virtual functions and dynamic allocation may degrade performance in high-throughput systems. Over-engineering. Misapplication in simple scenarios might unnecessarily complicate the code. Modern alternatives. Concepts like templates or const-expert can replace factory patterns in some scenarios. That was my video. I plan to create these videos each week. Follow me on Facebook, X, and LinkedIn. Check out theraycode.org and .com. Leave a comment, subscribe, and like. Be good. The Ray Code is awesome.